Okay, so now we have the today's last talk with Pazit Haim-Kislev from IAS. She's going to talk about the counterexample to Viterbo's conjecture.
Thank you for the organizer for organizing this very nice conference and inviting me to be a part of it. As the title suggests, I want to talk today about a counterexample to Viterbo conjecture, which is a joint work with Yaron, who's also here. So the plan for the talk would be to set a bit of context and explain Viterbo conjecture and why is it interesting and sort of a bit of the history of it, what's known. Then discuss the counterexample and maybe some questions and what's next. I'm going to start with the definition of symplectic capacity, which you've already seen this week, but as is the main object of this talk, I'll recall it. So it's a quantity which one can think of as the symplectic size. So it assigns a number to every subset of R to n. And because we want to think about this quantity, symplectic capacity, as a symplectic size, we define it axiomatically, and we want it to satisfy the following properties, which mean that it would be monotone with respect to inclusion, and even more than that, with respect to symplectic embedding. We want it to behave nicely with respect to rescaling. So if we rescale by alpha, the symplectic form is rescaled by alpha squared, so we want the symplectic size to be also rescaled that way. And third, we want it to be normalized. So we want the capacity of the ball and the capacity of the cylinder, which is a disk radius r, two-dimensional disk, times Cn minus 1, when I think about R to n as Cn, to be the same and equal pi r squared. So these three axioms are defining symplectic capacities, and it is in fact non-trivial to find such a capacity. And its existence would imply the famous Gromov non-squeezing, which says that this capacity sort of encapsulates the global invariant of the global symplectic invariant of a set. And this third axiom guarantees that this invariant does not come from volume. So two capacities which come from Gromov non-squeezing are the Gromov width, which asks what's the biggest ball one can embed inside your set, and the cylindrical capacity, which asks what's the smallest cylinder we can embed our domain into. And from the non-squeezing, we know that these quantities have a non-trivial answer. And they sort of try and enumerate this phenomenon of a global invariant seen by the non-squeezing. And from the monotonicity property, we immediately, and the normalization, we immediately get that for any capacity, we have that the Gromov width is the smallest one, while the cylindrical capacity will be the largest capacity there is. And so let's do an example to calculate the capacity of some domain. So if we consider an ellipsoid of the form sum of qi square plus pi square over ri square smaller than 1. So this would be an ellipsoid parameterized by Ri L1 to Rn. And this is when I think about R2n as having qi and pi coordinates. And up to some symplectic linear image, I can think of any ellipsoid in this way. And then I'm considering the biggest ball, which simply lies inside. I would get that this ball is of radius the smallest Ri one has here. And on the other hand, this ellipsoid simply lies inside the cylinder of the same radius. So using the fact that the Gromov width is the smallest and the cylindrical is the biggest, and the smallest Ri is both the Gromov width and the cylindrical, gives us that any capacity of this ellipsoid equals the minimum Ri square. Okay, but not every domain is so easy to calculate capacities. And in fact, since their introduction in the 90s by Eklund and Loffer, many other capacities were defined using various tools from symplectic geometry. So from Hamiltonian dynamics, generating function, Floor-Mildy, and so on. Not all relating to necessarily embeddings. And yet it gives you obstructions to embedding. Somehow it's very strong. But the difficulties of these capacities is mainly to calculate them. So we know to say their values on very few cases, which are very, very symmetric or very, very nice for some reason, like the ellipsoid. And subclass of domains for which we know a little bit more is convex domains in R2n, where in that case, many of the capacities are known to coincide with the systole with respect to the Reb flow, as discussed in this conference. So let me remind you what that means. So if I consider K in R2n, star-shaped, then the Reb vector field on its boundary, which is denoted by R, is known to belong to the kernel of the symplectic form restricted to the boundary of your domain. And I'm always working with the standard omega, so sum of dpi wedge dqi in R2n. And I want to consider sort of closed loops of this vector field, closed Reb orbit. And another way to think about this Reb flow is, so if I have my domain K and I look at a normal to that vector field, and then I look at the I times the where I is the thinking about orthogonal as Cn, would be tangent to your domain. So if that was my supporting hyperplane, and then I want the rep flow would be in this direction. So the rep flow would be parallel to J, the normal to K. And then my gamma would go along that direction. So let me remark that the rep vector, the rep flow on the boundary of such domains is well studied, and one can ask many questions which have an analog in the geodesic case, such as how many there are, their density, their equidistribution, and so on. And a lot of them are still open and not known very partially or not at all. But in the case of star shape and more specifically convex, we know that there exists at least one closed trajectory. And so we can discuss its the minimal overall closed, but the minimal of which quantity. So we want to consider the action of a loop, which be the area of the disk enclosed by the loop. And we measure the area with respect to our symplectic form, or equivalently, we can take the integral over the loop with respect to some primitive. So the lambda is omega, and the boundary of the disk is our loop. Okay, and the quantity we want to consider, or the systole, is the minimal action over all closed Reb loops on the boundary of K. And because many capacities coincide with this, and for historical reasons, because the first one to know to coincide were the Eklund-Offer and Offer-Zender, we would call it the Eklund-Offer-Zender capacity, previously defined in this conference as maybe the systole, and so on. Let me remark that this quantity, while we call it a capacity, is not exactly a capacity, because it doesn't satisfy monotonicity. It only satisfies monotonicity when it's restricted to convex domains. If I have two convex domain, one contained in the other, I can see that it's monotone, say using Clark dual action principle. But if I have an embedding of a symplectic embedding of one convex domain into the other, which is no longer convex, this is a way harder thing to prove, where it still remains monotone. And the only way I know to show that is using the fact that it's coinciding with other capacities, which for them we know. So whenever we think about this capacity, we need to restrict ourselves to domains which remain convex. Okay, so I guess motivated by the fact that a lot of capacities are known to coincide when restricted to this special case of convex domains, there was a kind of folklore conjecture stating that all capacities in fact coincide for convex domains. So meaning there is only one capacity. So if we know that the smallest one and the largest one are equal, then perhaps then we know that there's only one and the same as the ellipsoid case. And a related conjecture known as Viterbo's conjecture, states that kind of an isoparametric on the symplectic size, which says that the capacity of a domain with the right power so that this quantity would be homogeneous is maximized by the ball. Again, for K convex. So why am I saying it's kind of an isoparametric? So we said we think about capacities as size, and then if we take all convex domains with the same volume, then we want the capacity. This conjecture says that the capacity is maximized by the ball. And so calculating this quantity, we know that this is n factorial. And we can reformulate it in kind of a systolic inequality by saying, by considering the quantity, the capacity to the n divided by n factorial the volume, and asking whether this is always smaller than 1. And specifically considering the capacity which comes as the minimal over a closed Reb flows, we get a really kind of a systolic type inequality. Here. Now, let me maybe remark that the fact that we use the word convex here is somewhat strange. As we are talking here about a symplectic properties, a symplectic invariant quantities, and yet convexity is not a symplectic property and not being preserved under symplectomorphisms. So this is a bit of an odd thing to do. And in fact, we do not know how to express convexity in symplectic terms. So we do not know how to identify domains which has a symplectic image which is convex. This is like if you get a general domain and ask whether it has a symplectic image which is convex, it's generally a very hard problem. We do have some abstractions on this, so we know that not all domains have symplectic images which are convex, because there are several abstractions such as the Ruel invariant or the dynamically convex property, which I'll discuss later. But it's not fully classified yet. And so maybe if we draw analogs to the volume preserving or the Riemannian case, so if we would consider instead of symplectomorphism volume preserving, any domain has a volume preserving image which is convex. And in the isometry case of thinking about R2n as a Riemannian manifold, then convexity is being preserved under these kinds of maps. So symplectomorphism is somehow in between because of the richness of symplectomorphisms, we would expect to find a lot of non-convex domains which has images which are convex, but as I said, not all domains has, because there are some rigidity phenomena to that. The fact that I like this kind of question because I find that they kind of very elegantly and simply to formulate problems which encapsulate all of these maybe more deep questions. So why do we use convex and not something else here? Maybe you say, oh, you're just mistaking by taking convex, take something else. So let me remark that if we leave the set of convex and we go to a slightly bigger one, such as star shape, these conjectures are completely not true. So there exists a star-shaped domain such that the strong Viterbo conjecture, oh, I should say what I mean by that. Sorry. So remark, the Gromov width satisfy Viterbo conjecture. So why is that? As we said, this is kind of a systolic inequality, and the Gromov width asks what's the biggest ball one can embed inside. So it's easy to see that the ball is the best for that. And so because this is true for the Gromov width, if this was true, it would imply this immediately. So this is why I would call it sometimes the strong Viterbo conjecture. So there exist star-shaped domains with raw arbitrarily large. So how does this domain look? So if I look at a moment map, so a map from Cn, which goes to the norm of each of these complex coordinates, to Rn plus. And I take the point 1, 1, 1. Then I know, for some reasons, that if this point is inside, that the cylindrical capacity is bigger than pi or bigger than something. And I can take sort of an arbitrarily small volume of a star-shaped domain containing this point, and then look at the inverse of this map. And I would get a very nice, very symmetric star-shaped domain with arbitrarily small volume and a fixed capacity, so big capacity. This would mean that the systolic is arbitrarily large. And yet, when I go to the convex setting, I get something different. So it's a very classical fact that I can look at the biggest ellipsoids contained inside my convex domain. This is called the John ellipsoid. And then my domain would be contained in 2n times that ellipsoid. And because all capacities coincide for ellipsoids, we get that the strong conjecture cannot be too far away from being true. So it's true up to some constant. So it's already very different from the star-shaped case. And moreover, utilizing this similarity to ellipsoids convex domains have, especially when going to infinity in the dimension, Arshen, Avidan, Millman, and Ostermer were able to show that the systole is bounded by a constant to the n, where alpha is a global, independent of the dimension constant. So it seems that really, despite the fact that we don't fully understand, we need to use convexity here. What maybe other facts which are easy to see about the Viterbo conjecture is that, in fact, for any domain which is S1 symmetric with respect to the natural S1 action, when we think about R2n as Cn, we know that the strong Viterbo conjecture holds. So why is that? If we simply look at the biggest ball inside, the two boundaries must intersect at least at one point. And from the S1 symmetry, we must have an sort of S1 intersection. So it would bound some disk on a complex plane. So very much like the case of the ellipsoid. And when we project to that plane, it will give us that the projection of K is contained inside this disk. So this means that K is contained inside a cylinder of the same, with the same base as the biggest ball inside. So again, very similar to the ellipsoid, we get that all capacities coincide for this kind of domains. So very high symmetry gives us that it's the strong version holds. And in fact, for a bigger symmetry, for the torus symmetry one has, so one can even relax a kind of convexity and still get that conjecture holds. This is called like a monotone toric domain. So when the graph one has in this Rn plus is only decreasing, we say it's monotone. And then it was shown by Good, Hutchings, and Vinicius that the inverse of such a domain would satisfy that all capacities coincide, even though that it's not convex. Okay, and maybe another factor which I like in this context is that when the Gromov width, so the supermum in the ball we try to embed in the domain is attained, then actually the EHZ and the Gromov width are equal. So why is that? If the biggest ball we want to embed has a closed characteristic or a Reb orbit which lies entirely on the boundary, then we automatically get that the systole of the K, the domain we embedded the ball into, and the systole of the ball are equal. And so this means that the Gromov width and the EHZ of K are equal. And if no closed characteristic of the ball we try to embed lies entirely on the boundary of K, then we can actually use a result by Sullivan or even do by hand, construct some symplectomorphism which pushes all the points touching the boundary a little bit inside, which in fact would give us an embedding of a larger ball inside this domain. So this would be a contradiction to the fact that we took the biggest ball one can embed inside. So this feels like almost like a proof, and sort of maybe a kind of strong motivation to believe that the conjecture should hold, at least for this systole version of it. And maybe another notable result is by Abundandolo, Benedetti, and Edmeyer, which state that, as he mentioned in the talk, Alberto, not only the Viterbo conjecture holds in a C2 neighborhood of the ball, or Zols in general, also the capacities are known to coincide in C2 neighborhood of the ball. Okay. So as a consequence of the discussion on Zoll and the fact that we know that all smooth maximizers of the systolics must be Zoll, and all Zoll in our forest list are the ball, we know that if we have a maximizer which is not a ball, it has to be non-smooth. So maybe let me remark that despite that formally this quantity is not defined for non-smooth domains, because we are in the class of convex domains, using the monotonicity and homogeneity, we get that the capacity is continuous on the class of convex domains, which is not continuous in general. But when we are restricted to convex domains, it's continuous. And then there's a single way to define the capacity for non-smooth. And moreover, you can define it in the language of Reb. So you need to now generalize the notion of Reb to the non-smooth case, and then the capacity would still be equal to this minimum over generalized Reb. So what I mean by that is that if my domain is kind of not smooth and I hit a non-smooth point, so usually I'm moving in sort of j or I times the normal. But if I'm in a corner, so in a point which is not smooth, then now I need to move in sort of any direction which is I times a vector belonging to the normal cone of my domain. And that would sort of, so it means that it's not well defined, so I might have a choice here of the dynamics. But still, if I take the minimal action over all loops satisfying that the velocity belongs to at every point I times the normal cone, then I would get this capacity, this quantity coming from the continuity of capacities. So one might think that in the case of the non-smooth, it seems maybe even more complicated than the smooth case, because now the dynamic is not well defined, and you have choices when you get to non-smooth points. But it turns out that there is actually a simplification when we work with a polytope. So what I mean by that is that you can always find a simple action minimizing Lebowitz which is a piecewise defined loop gamma, which satisfies that it doesn't use speeds from the normal cone. So gamma dot is always some constant time j, the normal to the facet. So if that would be my normals to the facets, and 1 and 2, then gamma dot it's enough to look on velocity belonging to that. And moreover, it uses each of these only once. So the set of points where gamma dot is parallel to each of these gamma is connected. And sort of utilizing this and the fact that there are a finite number of facets, this means that there is sort of a finite number of options to minimizing loop to consider. And this means that there is a finite time algorithm to compute the EHZ capacity. Of polytopes. And I can, of course, approximate any domain with a polytope and then compute its capacity, but sort of maybe the difficult part here would be the running time, which will grow very fast with the number of facets. So this is still a very useful tool to increase our understanding of capacity because they're very hard to compute. And sort of this is in larger set of examples. Yep. And I should also mention a work by Chides and Hutchings, which gave a different algorithm to compute the capacities. Okay, sorry. To compute the EHZ in R4. Okay. So using these algorithms, of course, what we tried to do was to try and find counterexamples to these conjectures. And those attempts kind of failed. But more than that, they converge to equality cases, to the conjectured equality case. So some of them would be kind of 6 and 7 vertices. The simplex, so 5 vertices. So this is mainly in R4. And this could be actually proven. And rotations of the cube in the coarse polytope. And the standard simplex. Intersecting the cube. Why do I like this example? So how one gets to that example? So it's considering this intuition that one has that Zoll should be the maximizer. So why is that? Is because if I have some area which doesn't have an action minimizing orbits in it, I can sort of remove it and do not affect the capacity and still make the volume smaller. So an equivalent in the polytope case, so if I have my simplex, so the convex hull of the origin and the standard basis, then I understand the dynamics pretty well, and I know that no minimizer passes through the vertices which are not the origin. And sort of I can try and remove them a little bit, and it will not affect the capacity, and will remove the volume, so improve the systolic. So a lot like the motivation coming from Zoll. And I can continue doing that until I hit a minimizing or changing the capacity, so creating a minimizer, new minimizer. And I can do it for all vertices. And so in the end, I would get the intersection of this with the cube. And now this domain has systolic 1, or systolic volume 1. And now if I try, now this domain has minimizing orbit passing through every vertex. So I cannot find a trivial way to change it so that it would keep the same capacity and become smaller. So it seems like at least locally or under some conditions, local maximizers. But we do not know if this domain is actually symplectomorphic to the ball. It's actually whether this domain is equivalent to the ball one. So this is just an example for these kinds of attempt. Okay, so I guess this kind of maybe covers a little bit one approach to this Viterbo conjecture, which says that you can try and find dynamical property you would expect the maximizer to have. So this sole property may be a natural candidate. But another approach would be to try and explain what convexity means from a symplectic point of view. So, can you find an intrinsic symplectic terms for convexity which would classify convexity? So perhaps if we better understand what convexity contribute to this unique behavior of convex domains, it would be easier to sort of prove this, approach this kind of maybe more natural language. And one attempt for that is dynamically convex, which is a definition by Hofer, Wysotsky, and Zander. So we say K is dynamically convex if every orbit, closed web orbit, has a Conley-Zander index bigger than n plus 1. So Conley-Zander index is very roughly saying measures how much the nearby Reb characteristic spins around your loop. And somehow they also showed that in the convex case, they have to spin sort of enough times. So convex implies dynamically convex. So this seems like maybe a natural intrinsic property to define convexity. And maybe the hope was that if a domain satisfies that it's dynamically convex, it might be satisfying these properties for convexity, so which cause them to behave in a special way, or even more far-reaching, maybe all dynamically convex, so the converse is true. So all dynamically convex domains maybe have an image which is convex. But then Alberto, Bernie, Umberto, and Pedro showed that you can find a dynamically convex domain with the systole sort of arbitrarily close to 2. So this implies that either dynamically convex are not convex, or Viterbo conjecture doesn't hold. But then Chaidez and Edmeyer constructed an example for a dynamically convex domain which is not convex. So this kind of means that at least one of the options is not true. But as the titles say, now we know that also Viterbo conjecture doesn't hold. So I guess both are not true, and maybe we don't know much, I guess. Okay, so so what's the counterexample? So it's in every dimension. One has a domain in 2n. It's convex. And rho is bigger than 1. And the implication of that would be that also the strong version doesn't hold. So also the capacities do not coincide. So how does the example look? It's actually surprisingly simple. So it's a regular pentagon, a Lagrangian product with a rotation of the pentagon by 90 degrees. So this would be k times t, which is it would be kind of a billiard thing, which also appeared in the talk before, in this conference before. And we think about this product as inside sort of the imaginary part times the real part of C. And how one generalizes this into higher dimensions. Using some tensor trick, but if we just take the product, it would not be good enough. So it needs to be slightly more delicate than that. So we use the fact that for any two domains, if we take the one product of K1 and K2, Lagrangian product of now the Cartesian product of T1 and T2, it will be bounded by the systole of K1 Lagrangian product with T1 and K2 the Lagrangian product of T2. And by the one product, I mean the conval of K1 times the origin and the origin times K2. And using this, I could get a counterexample from the four-dimensional case in every dimension, which will remain a billiard and remain in the Lagrangian product setting. Yeah.
Is it just an inequality? It's not
Hmm?
It's just less than or equal to both.
Yeah, it's less or equal, but if the capacity of them are equal, then this would be equality, right? Make sense? Okay. Okay. So how does the rep dynamic look on this case? So So in general, how does it look in the billiard case? So as mentioned here before, it relates to the sort of Minkowski billiard one gets in one with respect to the different one. So if I start from some point in the boundary, I would move in sort of minus the normal. And then I would move in the here in the normal of that. And if I hit a corner, then I have a choice. And I choose any direction in the normal cone. And I move in minus that, and so on. Yeah, and this quantity, this dynamics is the lab dynamic, but moreover, it's the so this is Archanavidana Nostra. The capacity is actually the minimal billiard in K with respect to the geometry given by T. Okay, so let's now consider the dynamic one gets in this pentagon time pentagon. So we think about it as kind of a billiard thing. So it's enough to consider one of the pentagons. And remember that the geometry is being dictated by the rotated one, so by this one. And so for a general point, so say I'm on the boundary 1, I would move in a direction which is parallel to one of the edges. And I would reflect using the geometry dictated by here, but maybe an easier way to see it would be to notice that the disk enclosed by this pentagon actually shares normals with this pentagon, which would imply that the reflection law here is actually coinciding with the usual reflection law. So the reflection law coming from the standard one, so the angles are equal, which means that I can use sort of the nice unfolding technique. So instead of looking at the reflection of the billiard, I can look at the so maybe let me draw it here. So I'm looking at the reflection of that, and that would be this pentagon. And now instead of reflecting it, I'm continuing in a straight line. And now I'm reflecting it again. And continuing in a straight line, and so on. And how it would look in the unfolded case. So we would get kind of this movement, which would be a closed Reb orbit, so a closed billiard. It's not too hard to see from this, right? I'm reflecting it again and again, and then I'm getting sort of straight line connecting these two. And this means that sort of many or almost all points on the boundary are actually part of a closed trajectory. And this is sort of what's called a Besse trajectory, or a Besse domain, so a domain where all orbits on the boundary are actually closed. And the length of all of them is also the same. It's not hard to see, except for maybe if I'm in the middle, and then I'm closing only after half of the reflections. So it would be of half a length. And there is also an equivalent one if I'm doing one starting not from this point, but from here, and then my reflection would be slightly different. But I would also get a closed orbit in every point in a similar way. But interestingly, these are not the minimizing orbits. Kind of the minimizing orbit would actually be so some of them would look like this. So it would be two bounces along the diagonal, so going like this and then back. And in fact, they could also be going from a vertex and back to any point on the edge opposite it. And I would also have three bounces which are minimizing. So to see them, to see sort of all three bounces through this point, say, I'm considering the line parallel to the adjacent edges, and then all triangles contained in this cone. So, for example, this one would also be a minimizing orbit, but also that one, and maybe also a less trivial one to go around here, and then along the edge, and then back. So all of these would be minimizing trajectories. And when one calculates this, the length of this, one would get that this, the systole in this case is square root of 5 plus 3 over 5, which is roughly 1.047, which is, however, slightly bigger than 1. Yeah, and you might want to protest here that I said that, so the conclusion here that all minimizing orbit must pass through a vertex. So there's no minimizing orbit along sort of ordinary points on the boundary. So you might say, but you said that it's enough to not use normal cones. So you can indeed find orbits which simple, so they're not passing through, they're not using velocities from the normal cones in this setting, but they still remain in this degenerate phase. So it's a very somehow unique case. I don't know a lot of other examples where the minimizing spends time in high codimensions, but not using velocities from that. They sort of have to stay in sort of a low codimensions. And maybe let me remark that this kind of phenomenon of getting a basin closed and that the minimizing is not have to be out of this could be actually recovered using different regular polygons. So you can take different regular polygons, time its rotation by 90 degrees, and I would give you other examples for bases which are very, very unique. And so if we think about the cube, time it's rotating, so it would be the cube, so it's the polydisk, a known Besse, and if we take the rotation times the rotation by now 45 degrees, but it's also kind of very similar. This is known to be the ball. But if we take the simplex, time the rotated simplex, so as Yaron told us earlier this week, as part of their work with the Todo lattice, showed that this is actually the ellipsoid E12, also a Besse. So it seems that maybe worthwhile to study Besses which are not smooth, which are maybe not done so much up to today. Yeah, in the smooth Besse, it's also known that the ellipsoid is sort of the only, in our four at least, the examples for Besse. And I'm over time, so maybe that's just, let me just say that tomorrow Alexei would explain a little bit of where the example come from. So it's sort of attempting to consider what would be the best table for a given geometry. And I'll let him expand on that. And I'll finish up here. Yeah, sorry.